Hi, this is Jasmine and Chris, and we'll be demonstrating some chemistry problems for you today. We're going to start with problem 14 from the Chapter 1 worksheet. How many liters of wine can be held in a wine barrel whose capacity is 25 gallons, when 1 gallon equals 4 quarts, and 4 quarts equals 3.7854 liters? So we're going to start with 25.00 gallons. From here, we do two conversions, a conversion between quarts and gallons, where 4 quarts equals 1 gallon, and a conversion between liters and quarts, where 3.7854 liters equals 4 quarts. Notice we put liters on top because that's the answer that we want in the end. When we do the multiplication, we can cancel out 4 quarts in the first conversion and 4 quarts in the second conversion, since they're the same. So in the calculator, it would look like 25.00 gallons times 3.7854 liters for a final answer of 94.64 liters. Notice the final answer has 4 significant figures because the number 25.00 gallons has 4 significant figures. The conversion factors do not count as they are ratios. The next problem that we're going to be doing is from the Chapter 2 worksheet, and this is problem number 15, which is, which one of the following compounds is copper 1 chloride? We have the following 4 compounds here, and we'll go through each one to say why or why not they are copper 1 chloride. Let's look at A first, CuCl. By this we can tell that chlorine has a -1 charge and copper has a +1 charge. Using crisscross applesauce, we can tell that a subscript of 1 would be added to each, which would not show up in the final answer. This is conducive to copper 1 chloride, which says that copper has +1 charge, and we know that chloride has -1. Therefore, this is the correct answer. B cannot be right because using crisscross applesauce, it would note that copper has a +2 charge, which does not flow with copper 1 chloride. C cannot be correct either because this denotes that chlorine has a -2 charge, where it has a -1 charge in reality. And D cannot be correct because it denotes, using crisscross applesauce, that chlorine has a -2 charge as well. So, moving on to the last problem, which is from the Chapter 3 worksheet, number 19. Combustion of a 0.9835 gram sample of a compound containing only carbon, hydrogen, and oxygen produced 1.900 grams of carbon dioxide and 1.070 grams of H2O, or water. What is the empirical formula of the compound? So let's start with what we know. We know that compound X contains carbon, oxygen, and hydrogen only. We also know that when compound X combines with O2, it produces carbon dioxide and water. The first step to finding the empirical formula of the compound is finding the masses of C, H, and O. To find the mass of carbon, we start with what we know. The only carbon in the formula has to come from CO2. So we start with 1.900 grams of CO2. From here, we convert to its molar mass, and we use that information, and we convert again from the moles of carbon per moles of CO2 in the reaction. From there, we do a last conversion from moles of carbon per grams of carbon in each mole. Notice that we cancel out CO2 in the first conversion by putting it on the bottom. We cancel out moles of CO2 in the second conversion by putting it on the bottom. And we cancel out moles of carbon in the third conversion by putting it on the bottom. This leaves us with the grams of carbon in the end, which is 0.5185 grams. Again, notice that these sig figs in the answer match up with the sig figs in the original number, which is 1.900 grams. Now that we know the mass of carbon, we can go to the mass of hydrogen. We can start with 1.070 grams of H2O, as we know that the only hydrogen found is found in H2O. This equation will go exactly like the equation that we used to find grams of carbon. So we start with the molar mass of H2O, which is 18.02 grams of H2O per mole. From there, we move on to how many moles of H can be found per mole of H2O. This is 2 moles. From here, we go to how many grams of hydrogen or H can be found per mole of H, which is 1.01 grams hydrogen per mole. After doing these conversions, you'll find that the answer is 0.1199 grams of hydrogen. Again, notice how we match the sig figs and we cancel out the measurements or units that we don't want as we go along. Lastly, we'll use the same process to find the mass of oxygen. We'll use actually a different process to find the mass of oxygen because oxygen can be found in both of the products in the reaction. But if we already know the mass of C and H in compound X, then it stands to reason that to find the mass of O, we take the compound and subtract from it the mass of C and the mass of H. So we take compound X minus, which is 90.9835, and subtract 0.5185, and subtract again 0.1199. The final answer should be 0.3451 grams. And this is the grams of oxygen. Now that we know the grams of each component of compound X, we use another process to find the empirical formula. So we take each compound, starting with carbon, and we find its molar mass. So for carbon, the molar mass is 12.01 grams per 1 mole carbon. Notice that since we want moles in the end, we put it on top. What we're doing here is finding the moles of carbon, hydrogen, and oxygen in the compound. We do this again with hydrogen, 0.1199 grams, and we use the conversion 1 mole hydrogen per 1.01 grams hydrogen for an answer of 0.1187 moles hydrogen. And then lastly, we do it with oxygen, 0.3451 grams oxygen, multiplied by the conversion ratio of 1 mole oxygen per 16.00 grams oxygen, for a final answer of 0.02157 moles of oxygen. Now that we have the ratios, we use the smallest mole, which is oxygen, and we divide each mole number by it. So for carbon, we use 0.04317 divided by 0.02157. This comes out with an approximate number of 2. For these purposes, we can round to, a better number to use. So for hydrogen, we use 0.1187, which is its moles, divided by 0.02157, for an approximate number of 5.5. And lastly, for oxygen, we use 0.02157 divided by itself for an exact number of 1. From here, because hydrogen is not close to a whole number, we multiply by 2, because there are 5.5 moles for 1 mole of oxygen. From here, we can find that the formula is C4H11O2. The 4 from multiplying 2 by 2, the 11 from multiplying 5.5 by 2, and the O from multiplying 1 by 2. This leaves us with whole numbers that can be used for the empirical formula.